So you probably heard one of those news stories where in Australia they found a snake just just chilling in the toilet, right? Although this may be kind of scary to think about, it does demonstrate that a snake could go into very hard to reach places because it had to go through quite a journey to get to where it was. And so using this, we could apply this in robots. So we can use a robot to navigate through very narrow and complex terrain. So using this application, we could make robots so that it can replace human jobs that could otherwise be dangerous for them. And so in some applications, such as search and rescue, rescuers have to go through very unstable rubble to find potential survivors. And so what a robot snake could do is go through the rubble and find them, and the rescuers could determine the best way to rescue the person and not destabilize the already unstable rubble. And another application can be used for exploration of other worlds, such as Europa, where the terrain is not very well known, but a very versatile robot, such as a snake robot, could adapt to different kinds of terrain, as well as potentially swim underwater, where the underlying surface of Europa is mostly water, and it can be used to search for life, because many scientists think that there's a pretty good chance that life could be there, but we don't know yet until we explore it. And so what this does is that it allows humans to extend their range of perception without actually being there. So it's very useful in making rescuing or exploring more efficient and safe for humans, for them to not be put in the line of danger. And so for this summer, these are the goals I have for building the snake robot. So my first goal is to build a working model, which includes all the physics of it, how to control it, and have like a physical model in the simulation. The next goal is to mimic snake movement in nature, so that we could draw from nature to see how snakes adapt to certain environments and to change their gait in order to move the fastest way possible. And so once we have that, we can optimize speed and efficiency by measuring how fast it goes or how much energy it's using, and change certain parameters to see how we can make it faster or more efficient. And so what I'm going to go into next is the methods into building a working model. And what this all accomplishes is that we want to make the snake versatile in any kind of terrain, so it won't be stumped by some unexpected surface. And we want to make it robust so that no matter what it does, it could still try to accomplish what we want it to. And so, so for the first part, we want to simulate the physics of a system that a snake would be in. So this includes your force equations, your energy equations, friction, torque, stuff like that. And so by modeling the physics, we can build a model that could be accurate if it were to be in the real world. And so with that, we could program it to do different kinds of motions. And so in nature, there are 4 different kinds of motions that snakes do depending on where they are. So the rectilinear is mostly used in narrow environments where it inches forward by curling its body and inching its way forwards bit by bit. The serpentine is your typical sine wave motion where it uses the curves of its body to push off the ground and propel forward. And the concertina method is similar to the rectilinear, but it can be used in wider spaces where it anchors the bottom part of its body and pushes it forward, and then anchors the top of the body and pulls it forward. And so what these blue areas represent are where it's applying more pressure, and the sidewinding also uses this method where the snake lifts part of its body and pressures parts of its body. And in sand, it's very shifty and loose, so snakes have adapted to moving through this really shifty terrain. And so you can see that parts of its body are on the ground, and it pulls parts of its body forward and anchors parts of its body, and so it's able to take advantage of its the friction in some places and move parts of its body in order to move forward. So we could program these different motions by simulating how friction works on snakes and by lifting parts of its body. And so those are the methods for goals 1 and 2, and I want to go into the methods for optimizing the speed and efficiency. So we're going to start with a method of locomotion in any kind of terrain. And so we're going to simulate it to go through the terrain, see its interactions with the environment. And with that, we can measure the speed and energy consumption of the snake. And using these two things, we can see whether or not the methods need to be improved, or if we need to use a different kind of method of locomotion to go through this type of terrain. And with this cycle, we can make more and more improvements and fully optimize how the snake can move through environment in the fastest way and the most efficient way possible. So to get started with all this, I use animations every day to see whether or not the simulation makes sense and that it has the right physics involved, as well as doing it what I want it to do. So to take a very simple case, in a frictionless case, we can look for two different things in terms of the physics part of it. We can look for where the center of mass is and the conservation of angular momentum. So if we know these two things are correct, we can move forward and seeing that our physics is correct, so we can do further simulations knowing that we have accurate results. And so in the first example, you can already see that the little circle represents the center of mass, and the line represents the snake links. And so you can see that it's already wrong because the center of mass should be in the middle of the snake link. But another thing you can see after it stops moving is that it continues to rotate, which doesn't conserve angular momentum because in a frictionless case, you don't really have anything to push off of in order to keep rotating. So you know these two things are wrong, so you could go back and see what bugs you have and to improve the model. And so this is the corrected version, and you can see that the center of mass doesn't change because there's no friction to move the center of mass around, and it doesn't rotate afterwards, which is a good indicator that conservation of angular momentum is conserved. And so with that, we could use intermittent friction, which is basically using friction in different places at different times in order to achieve movement. And so in the accordion or the concertina method, where it pulls forward and pushes forward based on, it pulls the front forward and pushes from the back, we can use that model to show that we can use a scrunching method to inch forward. And also, another example of how we can use friction to move is the robo method, where it's kind of like rowing backwards on a boat, where you can move based on pushing off the floor or the sides of the floor to generate movement forward. And so, from this, we can make a couple of conclusions. So the first part, we know that the simulation is correct in all the physics from the first example that I showed you, and that we could move forward confidently knowing that the physics is correct and that all our simulations are accurate. And with the second example, we can know that we can use friction as a way to move forward, although a lot of times we think of friction as a way of dragging things down. But when we can incorporate asymmetrical friction, as snakes do on their scales, to move forward in a faster manner. And so knowing all of the simulation parameters, we can measure how much power we're putting into the joints and the velocity it's moving. And we can use this to find the best solution in any terrain, which I showed in the optimization methods example. And so we could use asymmetrical friction and lifting different parts of the body as real snakes do to achieve certain movements. And In the other examples, I use inputting torques as a way to move, but my professor came up with a way that we could just say what the snake we could just program what the snake wants to do, and we can measure the power and speed later. So this is an example of serpentine motion, and so you can see that I don't know if you guys can see, but the red parts of its body are where it's pressuring the ground, and the blue parts are where it's lifting parts of the ground. So using this, we can model how a real snake moves using different, kind of like sine wave motion, but this is more of a half circle motion. And depending on how fast we can propagate the wave through the snake, we can achieve the side winding action where, we can achieve a side winding action where it uses different parts of its body to move diagonally as a real sidewinder would. And so, knowing how we can implement asymmetrical friction, we can optimize what coefficients we can put in the forward direction, backwards direction, and side direction. And so what this graph shows is that as we lower the forward okay, so as we lower the coefficient of forward friction and increase the coefficient of backwards and side friction, we can see that it can travel a further distance, which is a good indicator of speed because all the simulations are running through the same time. And so we don't want to